Okay, another example is the Flixborough in England in 1974. So this is also caused by um, unsafe act by these workers in this plant. So what happened is, so the Flixborough plant had 6 reactors. Okay, so it has reactor number 1, 2, 3, 4, 5, 6, and then one of the reactors was it was malfunctioned. So they took out the reactor, and then they still wanted to run the operation. So somehow they connected reactor 4 and 6, and also because they wanted to save costs, they connected these 2 reactors using a insufficient length of this connection, and that it's a wrong type of connection, and then that connection failed and caused an explosion. Okay. So you can read more about it. It's actually from this website. So what happens is at around 4:50 p.m. on a Saturday. So 4 o'clock on a Saturday, it's as people don't really work, it's a half day, right? In 1974, the explosion killed 28 workers, and then 36 people were injured. The number of casualties would have been more if the incident had occurred on a weekday, because it happened on a Saturday, so the main office block was not occupied. And then off-site consequences resulted in 53 reported injuries, and the properties in the surrounding area was also damaged to a varying degree, because they were houses also near the this plant. And prior to the explosion, it was discovered that there was a vertical crack in reactor number 5. So reactor 5 had a crack, and it leaked cyclohexane, and they had to shut it down for an investigation. And then after that, the investigation that followed identified a serious problem with the reactor. And then they decided, okay, we removed that reactor 5, and let's install a bypass to connect reactors 4 and reactor 6 so that the plant can continue to its production. But then that bypass system is a 20-inch bypass system. It ruptured, and it has caused the rupture may have been caused by a fire on a nearby 8-inch pipe, and that resulted in an escape of a large quantity of cyclohexane. And that cyclohexane formed a flammable mixture, and then subsequently it found a source of ignition, and then there was a massive vapor cloud explosion and caused extensive damage and started numerous fires on the site. Okay, so 18 fatalities occurred in the control room. It's because the windows shattered and then collapsed the roof. So 18 people in it, everybody died because nobody was able to escape from that control room. The fires burned for several days, and after 10 days, those that still raged were hampering the rescue work. The failings in technical measures is because they did plant modification without a full assessment of the potential consequences, and they limit their calculations on the integrity of the bypass line. They had no calculations done for the dog-leg shaped line, or for the bellows. It's the connection that they used. They didn't do any calculation for that, and they didn't also propose any drawing, okay, for that modification. Okay. So they didn't follow the procedures, no heads up, and then they used this flexible pipe, okay, which they shouldn't use, and they didn't do any pressure testing when they installed the pipework modification. And then when they did recommissioning, probably they didn't even follow the maintenance procedures and so many other things. And also another concern is the plant layout. So the layout of the buildings in the plant was just too close together. So the land is not big enough, and they had a lot of buildings packed in one area. And the design of the control room also could have been designed better, okay, to withstand major hazard events. So the structure of it was just not properly designed. And then many other things, they didn't have inner thing and so on. So this is why you have to take a lot of action to prevent hazards or fires and explosions from happening. Okay, unconfined vapor cloud explosion. Unconfined vapor cloud explosion is an overpressure that happens when a gas cloud detonates or deflagrates in open air rather than simply burns. So it happens in open air. Okay, so what happens to a vapor cloud? So when you have vapor cloud, first of all, it's very rich. If it's very rich, that means it's above the upper flammability limit. And then it starts to spread and disperse. So once it starts to spread and disperse and mix with air, and then it goes into the flammable range. Okay, if you're lucky, and then it will be in a range that it is too lean for it to become flammable. Okay, so you have this range of flammability. You have the flammability range, you have the too rich and the too lean. So normally the edges will start to burn through deflagration, which is a steady state burning. And then the cloud will disperse through natural convection. The flame velocity will increase with containment and turbulence, because in a process plant you have different buildings, different structures that causes turbulence in the air, okay? And then increases the velocity of the flame. And this high velocity is high enough that will make that cloud detonate. Okay? If the cloud is small enough with little confinement, it cannot explode. So if the area is clear, not much structures, okay, not many confined space, it cannot explode, okay, because it has that small cloud. Okay, it has to have a big enough cloud with high velocity and in confined space, then it can explode. Okay, so when you have confinement, okay, you have all these buildings, structures, vessel, tanks, all arranged in a compact space. It prevents the escape of that vapor. So therefore, it increases the turbulence of the wind in between those structures. So that can cause high overpressure. And the cloud composition too is another factor. If you have unsaturated molecules, because all ethylene clouds explode, cloud composition with low ignition energies or high flame speeds. And a good weather also, let's say the weather is stable, low wind speed, no storms, no high wind, that can cause the vapor cloud to reach overpressure. And also, if you have a large vapor cloud, there's a higher probability of it to find an ignition source, and it's more likely to generate overpressure. And then finally, there should be a source, such as a flashing liquid, high pressure, large, low or downward facing leaks. These are sources of leaks that can cause the formation of a vapor cloud. Alright, so vapor cloud explosion, some of parameters that affect vapor cloud explosion behavior, the time and the quantity of material released and vaporized, is it during the daytime, during cold weather, hot weather, how much is being released, and the time span from the onset of the leakage until the ignition, is it a short time or a long time? The configuration of the space where the leakage took place, so is it in a very tight and confined space? And probability of ignition of the cloud, where is the position of the ignition point, for example, and how many ignition sources are there? And then the distance that's traveled by the cloud before it reaches the ignition point. So how long does it have to travel? So the longer it travels, then it becomes it can become lean. And then also the efficiency of the explosion. What is the percentage of efficiency of the explosion? And studies have shown that ignition probability increases as the size of the vapor cloud increases. So the bigger the vapor cloud, the ignition probability will increase because it has more chance of meeting an ignition point. The explosion efficiency is normally small, about 2%, 2-3%, yeah, not very big. The turbulent mixing of the vapor and air and the ignition of the cloud at a point remote from the release increases the explosion impact. See? So that's why it's the separation of the structures will cause the turbulent mixing, making it more effective and cause the explosion. Okay, TNT Equivalency Method. According to this method, the power of the vapor cloud explosion equates to an equivalent mass of TNT that will produce the same explosive power. So this is the equation to determine the mass of TNT that is equivalent to the vapor cloud explosion. Okay, so M is the equivalent mass of TNT. Is equals to the empirical explosion efficiency, because I mentioned just now what is the efficiency of the explosion. M is the mass of hydrocarbon multiplied by 1 over molecular weight of that hydrocarbon, because you want to get the moles, and then you multiply with the heat of combustion or the energy of explosion, and divide all of that with the energy of explosion of TNT, which is 4,686 kilojoule per kilogram. Okay. So the explosion efficiency is one of the major problems in the equivalency method. Okay, so that new just now. The method calculates the overpressure of an explosion without taking into account the space configuration where the explosion takes place. So it doesn't really take into account what is the degree of confinement or congestion. Is that explosion is in the middle of an area full of equipment, or is it in a closed space? Because these things will actually exhibit different power from an equivalent one in an open space. Okay, so that's the disadvantage of this calculation. It doesn't take into account of that, so the estimation may not be very accurate. Okay, so, but the advantage of this method is just it's very easy to calculate. Okay, it's a simple calculation. Okay, and procedure to estimate the damage associated with an explosion using the TNT equivalency method is, first of all, you determine what in the explosion, how much hydrocarbon is there, how much of flammable material is there in the first place, and then after that you estimate what is the efficiency of the explosion, and then you calculate the equivalent mass of TNT. So the explosion efficiency is normally estimated, is normally taken as 2%. And then you use the scaling law to estimate the peak site on overpressure, the PSO overpressure. And finally, you estimate the damage for the common structures and process equipment. Okay, so you take note that the procedure can be applied in reverse to estimate the quantity of material involved based on the damage estimates. Okay, you can use this also. Okay, let's say you have 1,000 kilograms of methane that escapes from a storage vessel, and then it mixes with air and then it explodes. So find the equivalent amount of TNT to this 1,000 kilogram of methane, and then determine what is the site on peak overpressure at a distance 50 meters from the blast, and then estimate what is the possible impact to the structure. All right, so we assume that explosion efficiency is about 2%. Okay, so let's do the calculation. So we use the previous calculation. The mass of TNT is the efficiency of the explosion times the mass of the hydrocarbon times the 1 over molecular weight of that hydrocarbon times the heat of combustion of that hydrocarbon divided by ETNT. ETNT is what was the ETNT just now? 4686, right? (4686 kilojoule per kilogram). Okay, let's go back to the examples now. Okay, methane, and we're doing methane now. So this is 4686. Okay, so 1,000 kilogram of methane is equivalent to 214 kilogram of TNT. And remember the previous equation, this the scale distance equation that we used. So we use this scale distance equation to find the scale distance. So the distance is, how far are we from the source? Going back, 50 meters from the blast. So we are 50 meters from 1,000 kilogram of methane. So 1,000 kilogram of methane, we determined already the equivalent amount of TNT, and we found that the equivalent amount of TNT is 214 kilogram, and so therefore ZE is 50. So this is 50 divided by 214 kilogram of TNT to the power 1/3, and you get 8.4. And now what do you do next when you have the scale distance?
Go refer the chart.
Refer to the chart, that's right. So you refer to the chart, you read 8.4. When you read 8.4, 2, 3, 4, 5, 6, 7, 8, I think it's somewhere around there. Okay, and then you go up, see, and then you read here it's about 0.25. Okay, so your scale overpressure is 0.25, and then you can calculate what is the overpressure, which is the scale overpressure times the atmospheric pressure, and you get the overpressure of 25.3 kilopascal. So that is a big number. And remember this table, so we look back into the table. Once you see a double digit like this, it's always serious. So 25.3 is partial collapse of walls and roofs of houses, and there's possibility of having a destruction of the houses. Okay. Maybe partial destruction of the houses. So what can you conclude? 1,000 kilogram of methane it can damage buildings. Okay. Methane CH4. We think that methane is well, we use methane a bit, right? But 1,000 kilogram methane, is about 214 kilogram TNT, and that can cause the house partial collapse of walls and roofs of house, even if you are 50 meters from it. Okay. Now there is another method called the TNO Multi-Energy Method. So this method, it takes into account the confinement around the area of that vapor, the vapor cloud formation. Okay, let's say in a congested area. And this method suggests that the damaging explosion can only occur when flame acceleration takes place within a plant structure, because a truly unconfined explosion is very unlikely to occur. There's always a lot of these obstacles that limits the dispersion of the vapor cloud. Okay. So the basis of this model is the energy of explosion depends highly on the level of congestion and depends less on the fuel in the cloud. Okay, so it really depends on the congestion, not on the amount of fuel. So the main factors that affect vapor cloud explosion in chemical plant structures is the turbulent effects. Okay, it causes the acceleration of the flame speed as the flame passes the obstacles in the plant structure, and eventually giving an explosive of overpressure effects. A highly congested plant structures give high overpressures, and flammable gas with high laminar burning velocity will give high overpressures. The degree to which leaks of flammable gas fill a structure, meaning the larger the volume of structure, will give a higher overpressure, and longer flame path then through the structure and will give higher overpressure. Okay, so because it takes a long time for it to move and disperse, so you have a higher chance of getting overpressure. Okay, so to use the TNO multi-energy method, this is how you do it. So first of all, you have to determine what is the charge combustion energy E. And then you multiply the confined volume occupied by the vapor cloud with the heat of combustion of hydrocarbon air mixture, which is 3.5 times 10 to the power 6 joule per meter cube. And then you estimate the blast strength about between 1 to 10. Determine the Sachs scale distance through the following equation. So that's the equation. And then when you get the Sachs scale distance, you can find the Sachs scale blast site of overpressure from a blast chart. So the Sachs scale distance, this equation here, R prime, equals to the distance from the source, this small r, divided by the charge combustion energy E over the atmospheric pressure to the power 1/3. So this is a bit different from the previous equation that we calculated for ZE, remember, or the ZE. Remember that one is distance divided by the mass of TNT. So we don't want to use the mass of TNT this time because it's too simplified and it doesn't really give a correct estimation. Now the R prime here is the Sachs scale distance. R is the distance from the charge, and then E is the charge combustion energy. To get the charge combustion energy, you have to multiply the confined volume occupied by a vapor cloud with the heat of combustion of a stoichiometric hydrocarbon air mixture, which is 3.5 times 10 to the power 6. And then that is the ambient atmospheric pressure. And power 1/3. And once you have the SAS scale distance, the R prime, you can find side on over pressure, okay, delta PS, okay, the PS here on the y-axis, and if you read it, okay, depending on the strength of the explosion, and then once you have the PS, okay, you can find the overpressure by multiplying with the ambient pressure. Okay, now let's try this example. Consider an explosion of a propane air vapor cloud. So propane is C3H8. So propane air vapor cloud is confined beneath a storage tank. The tank is supported 1 meter off the ground by concrete piles. The concentration of vapor in the cloud is assumed to be at stoichiometric concentration. A cloud of 2094 meter cube confined below the tank, representing the volume beneath the tank. So this is the volume of that vapor cloud beneath the tank, is 2094 meter cube. Determine the overpressure from this vapor cloud explosion at a distance of 100 meters from the blast. So distance is 100 meters, so this is R. Using the TNO Multi-Energy Method and assume a blast strength of 7. Okay. So what is happening is you have a storage tank, and then somehow, I guess the storage tank has a leak, and then you have propane at the bottom of the tank, and then that propane vapor is mixed with the air, and then the area underneath that tank, which is a confined space, is about 2094 meter cube. Okay, and then so let's say you are standing 100 meters from that vapor cloud formation under the tank. Calculate what is the overpressure that you can feel 100 meters from that tank, and assume that the blast strength is 7. So first of all is you calculate the E first. So the energy is the volume underneath that tank, which is 2094 meter cube, times the, what is this? What is that thing is now? 3.5 times 10 power 6. That's the stoichiometric hydrocarbon air mixture. Okay, so 3.5 times 10 to the power 6. And then once you get E, you find you can calculate the SAS scale distance. Okay, so the SAS scale distance is R, the distance from the source, which is 100 meters, divide by the energy that you have calculated before. Okay, this energy is divided by the ambient pressure, 101,325 Pascal, and the whole thing is power 1/3, and you get an R prime of 2.4. And then with this R prime, you go to the blast chart. Let's go to the blast chart. Okay, 2.4. Oops. Okay, so 2.4 is somewhere around here. So if this is 2.4, you go up and reaching somewhere about 2.4, somewhere about here, I guess. Okay. That's not really the right arrow. And then you read to the side is 0.13. Somewhere here, it's estimated as 0.13. Let's see. Okay. So we read from here because the blast strength is 7. So that's why we picked this 7. Okay. And then you calculate what is the overpressure, which is the scaled overpressure 0.13 times 101.3 kilopascal, and the result is 13.2 kilopascal. Go back to the chart and see what kind of damage that can happen from this much overpressure. Okay. You can try this tutorial. Let's say you have 1,000 kilograms of butane. So the previous example was how many kilograms? No, the previous example is not 100 kilograms. It gives you the volume. Let's say 1,000 kilograms of butane escape from the storage vessel, mixes with air, and explodes. Determine the equivalent amount of TNT and determine the site on overpressure at the distance 60 meters from blast. Estimate the possible impact of the structure. Did we do this just now? Seems like we did this already. Okay, so this is equivalent amount of TNT. It's not the TNO method. Okay, so to find the equivalent amount of TNT, so you use ZE equals to R mass TNT. Okay. So how do you find the equivalent amount of TNT just now? Do you remember? How do you find the equivalent amount of TNT? From 1,000 kilograms of butane? Do you remember?
Use the TNT Equivalency Method.
How many?
You have to use the TNT Equivalency Method. The one 1 over MW.
Alright, so it's yeah, so you use this TNT equivalency method. Yes, this one. So you use this equation. So you need to know because we know the mass of hydrocarbon, and with that hydrocarbon, you know what is the molecular weight, and then you can find the energy of heat of combustion. The heat of combustion can be found in many books, thermodynamic books, for example, or online, and you can get the mass of TNT. Okay, so going back to okay, and then there's also another example here. Consider explosion of methane air vapor cloud confined beneath a storage tank. The tank is supported 1 meter off the ground by concrete piles. The concentration of vapor in the cloud is assumed to be at stoichiometric concentration. So this is the TNO method, because you're given the volume. It's confined below the tank, and then you have to determine what's the overpressure. Find the overpressure from this vapor cloud explosion at a distance 100 meters from the blast. So this is your R. Using a TNO Multi-Energy Method, assume the blast strength of 7. You can try this too at home. You're already at home. What do I mean is you can try it at your own time after the class, because I'm trying to finish this. Okay, so the next topic is about BLEVE. BLEVE. Now, what is a BLEVE? A BLEVE is an acronym for boiling liquid expanding vapor explosion. So you have a boiling liquid, and then it expands a vapor, and then you have an explosion. So this is a result of a liquid within a container, normally a liquid in a tank, and then the liquid reaches a temperature above its boiling point at atmospheric temperature, and then it causes the vessel to rupture into 2 or more pieces. A BLEVE can occur when a fire impinges on the tank shell at a point or points above the liquid level of the contents of the tank. So that impingement will cause the metal to weaken and fail from internal pressure. So let's say in this diagram shows that there's a fire close to this vessel. Let's say this is a spherical vessel, a spherical tank. And then the fire nearby this tank will cause the pressure in the tank to release, okay, because it heats up the liquid in the reservoir and the shell of the tank. And then the pressure release will cause the structure of the tank, the metal will be weak, and then it ruptures. So once it ruptures, it liberates the vapor out, and then if it reaches an ignition point, it will just explode and form a ball of fire. Okay, so BLEVEs can also be caused by external fire near the storage vessel, causing the heating of the contents and pressure buildup. So such explosions can be extremely hazardous, and BLEVEs can also result from mechanical damage to a tank as well. For example, that damage is not because of that fire. Let's say that the tank already has some kind of damage. Let's say if it's a tank on a truck, for example, or on a train, let's say the train derailed or the truck got into an accident, and then it causes the tank to I don't know, like have some kind of damage on the shell of the tank, and then once there's pressure buildup inside, and then it can cause the explosion. So when BLEVEs occur, the debris from this kind of explosion can travel hundreds of feet at tremendous force, and the escaping fuel can ignite and expand and cause a fireball. Okay. Now, if the vessel is ruptured, that vapor portion inside that tank will leak rapidly, and therefore it lowers the pressure inside the container. Okay, because once the vapor release, the pressure inside will suddenly becomes very low. So when that happens, the sudden drop of pressure inside the container will cause a violent boiling of that liquid, which rapidly liberates a large amount of vapor in the process, and then can cause a fire if it meets an ignition point, ignition source. So the pressure of this vapor can be extremely high, causing a much more significant wave of overpressure or an explosion. And that can completely destroy the storage vessel and projects the fragments over the surrounding area. And if the substance involved is flammable, it is likely that the resulting cloud of the substance will ignite after the BLEVE has occurred, and then it forms a fireball and possibly a fuel air explosion or a vapor cloud explosion. And if the material is toxic, a large area will be contaminated. So the most common type of BLEVE is caused by fire. And the steps on how it happens is as follows. First of all, you have a fire. You already have a fire that had developed adjacent to a tank that contains a liquid, a flammable liquid. And then that fire, it heats up that wall of the tank. So once the wall of the tank is heated up, what happens is at the bottom of the tank is always filled with liquid. So that liquid filled portion stays cooler than the top part because of the heat sink effects. But the steel around the vapor space at the top part is being heated up rapidly. So if the flames reach the tank wall or roof where there is only vapor and no liquid to remove the heat, the temperature of the metal tank would rise up until the tank would lose its own integrity and structural strength. And then the tank, the metal will start to rupture and then explosively vaporizing its contents. So often the boiling of the liquid and the burning of that liquid behaves as a rocket fuel. So it propels the vessel parts for a great distance. Let's watch this demonstration of a BLEVE.
When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure. As pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion. The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion. Tank sections containing rapidly igniting fuel can become flying missiles, traveling great distances, causing secondary fires and other damage. It all happens quickly and with little warning.
Really fast, understand? But take note that is in an open space, so that is why it happens really rapidly, and it's gone after the whole thing has exploded. So normally it's not. This is not the case. In reality, tanks are always in a complex of a lot of tanks. So you have this confined space. So therefore you have multiple explosions happen after it happens after one after another. Yeah. So that was a very good demonstration, and we have reached the end of the slide. So let's do a bit of summarize what we have covered. So we have covered blast wave, shock wave, injuries due to explosion, parameters of explosion behavior, detonation and deflagration, and we have calculated overpressure, and then we also estimated the blast damage from overpressure. We used the Probit equation to estimate the impact of explosion, and then we looked at VCE, vapor cloud explosion. We used the TNT Equivalency Method and the TNO Multi-Energy Method, and finally we covered BLEVE, and that is the end of this slide. Thank you very much.
Thank you, Dr.
All right.